I should thank you for the organizer for inviting me to give this report and show what you are doing and trying to understand a little bit of molecular fragmentation of complex molecules. So here a little bit of background. This community and myself has been working for many years in trying to understand several channels in collision with electrons, protons, and heavy ions. These channels, the experiments has been done mostly, in the large majority, with atoms. Normally in gas phase, and some small molecules. The fact that atoms are very nice and friendly instead of molecules or complex molecules is because it's easy to measure the final state, the final charge state. With the final charge state of the target known, we can make coincidences with the projectile, with the ejected electrons, and identify and study more deeply the dynamics of all these processes. They are sometimes very complex, so the fact that you use atoms, and the atoms has a final state well-defined, the final charge state well-defined, is make the analysis and the study much more reliable. When you go when you make the collision with complex molecules, we have trouble because the target breaks apart in many pieces. And we don't know how to identify the final target charge state from the fragment ions observed. We have a lot of fragments, and then we don't know how to identify, measuring only that fragments, which are the final state. So you get a little bit lost to identify all these processes. And for simple molecules, like small molecules, H2, CO, N2, etc., this is relatively, it can be done with double coincidences and things like that. But for large molecules, this is almost impossible to do in this way. So this report, I show some force to try to identify the final target ionization state from the fragment ions observed. So that's the overview of the review of the talk. In this graph, I always use 4 molecules. Water, because many people here have been working with water. It's simple, has few molecular orbitals. So this is CFC, which is methane-like, have more orbitals. And these 2 ring benzene-like isomers, the pyrimidine and pyridazine. The pyrimidine has 2 nitrogen, this green, the green guys here, separated by a carbon. And the pyridazine is the same, but with the 2 nitrogen close together. So these are 2 isomers, C4 and 2H2. So this, you see that this increases the complexity. The number or density of the states increase, and at some point we have so many orbitals to follow and to fragment the molecules that you have some kind of, you need some kind of organization to do the job. So the idea is I will separate the molecular orbitals in 2 groups, one which we call outer valence shells, and the other inner valence shells. And what are the boundary between these 2? It's completely arbitrary, and I define the boundary as the orbital in which the Auger decay is energetically allowed. So if you increase the complexity of the molecule, this is going to be almost a continuum of orbitals. So you need to define something to separate single from double ionization. So the outer valence shells, normally they generate the parent ions, the most abundant fragment ions, and I will show that it's possible to obtain a direct relationship between the active orbital and the fragment ions. When you go to the orbitals where the Auger decay is accessible, then you have double ionization. You start to see some fragments that you don't see if you make vacancy here. And you have two processes competing, the Auger decay and the prompt decay. And also, you have the competition with projectile double ionization. So some fragments here are only produced by double ionization. The question is, how can we identify easily this fragment and know if we are in double or single ionization? So I always start with water, because it's a simple one, and go to the more complex. I start first looking for the outer valence shell, then I go to the inner valence shell. So that's going to be the outline of the talk. Okay, here are water. I put in this side the fragments, possible fragments that can obtain, and this side the orbitals. Here there is a connection. It is relatively well known. And you can see that for some products, it can come from two orbitals or more orbitals. On the other hand, you have some orbitals which generate several fragments. So you have fragments that are generated by more than one orbital, and you have orbitals that generate more than one fragment. So we have an intercrossing between the fragments and the orbitals. And if you assume that this relationship can be done in a linear way, you can find a relationship between the cross-sections for the fragment ion production and the cross-section for the vacancy production through a matrix, which I call a fragmentation matrix. And these numbers can be arranged in the matrix form. In the matrix form, you have the cross-sections for the vacancy production, the cross-section measured, this is calculated, that one are measured, and then this number are filled empirically. There is almost no calculation to fill this fragmentation matrix. This number cannot be found theoretically. A few attempts has been tried, and I mentioned the Suarez that presented posted Wednesday, which calculates the 1B2 fragmentation, this number here from theory. Okay, but well, in fact, it's the unique case I know. So this must be done empirically, but you need information from theory, and you need information from experiment. One side you have to have the theory, and the other side you have to have the experiment to fill this up. Okay, back. So having this fragmentation matrix, I need the vacancy production to obtain or to compare with the products that I measure, that's measured. So this community can know how to do it. There are several people here that know how to do the calculation. But because I want to apply this to several molecules, I am using a semi-scaling that works from hydrogen to uracil or anything, but this is not really important. In fact, this is just as a guide. We do need much better calculation for that, but I'm using this because I don't have another one. And here's a new comparison with this scaling with the calculation from Champion and co-workers from pyrimidine to show that it works. Okay? It's not perfect. It works reasonably. Okay, so you have the cross-section here for the vacancy production. You have the fragmentation matrix. Then you can get the products. I put here the only two, and I call attention that for these two products, the cross-section has a shape. You see that's not perfect here. And here is not perfect for two reasons. Because the model is not good enough, the scaling, and because there are other processes for inner shells that I show you in a moment. Okay, but what I call attention is that this curve has a unit concavity. It's a negative concavity, okay? There is no change in shape. These two curves have negative concavity. And that will be a signature for fragments that are produced by outer shells. Okay, let's go to another more complicated. So I apply the same methodology. I will not repeat. So it gets more fragments. You have more orbitals. So you have more things in the elements in the fragmentation matrix. But if you do the same thing, same methodology, so you get a good reproduction of all or most of the fragments. Now I go to the pyrimidine. Still more. I just put a few here because there is no space. Let's go to the other floor. If I put all the fragments. And here, the orbitals, and this is messy relationship between the orbitals and the fragmentation. But these numbers can be better organized in the fragmentation matrix. In fact, the fragmentation matrix can be a very good and useful way to store the information of the fragmentation. If this is calculated for one energy, if you change the energy, you change this number because you change the cross-section for vacancy production. And of course, you change the yields of the fragment, but you do not change the matrix. If you go to electrons or go to protons, or if you go to photons, there is no reason why this fragmentation matrix change. You're going to change the cross-section here. You're going to change the fragment yields here, but this should be the same. There is an assumption here, is that the collision is fast enough that the molecule go apart, break apart, in a time much longer than the collision time. The collision time is typically attosecond in the attosecond regime, and the fragmentation time is a femtosecond regime. So for 100 or 200 electron volts or some MeV protons, it fits well. Okay. Okay. Another comment is that this is number that I generated with the scaling. If a beta theory is calculated, if this vacancy is calculated with beta theory, this number will change, and this number also will change. Also, if someone did experiment and get another set of values, that's very common. Different laboratories have different. These are absolute cross-section. That's important. So absolute cross-section is hard to get. So it's not uncommon to have a difference, considerable difference between measurement in different laboratories. This number won't change. So to have a reference, a real reference, we need a collective, let's say, way to build this. So several people should, at the end, reach a consensus about this, this number. Okay, so this is pyrimidine. Now we can go to the fragment ion cross-section, and I put here the two isomers, the two pyrimidine and pyridazine. Now you see that these are the larger cross-section fragments, the more abundant fragments, and they have the same shape. They are only one concavity. That's one observation about these two. That doesn't matter if this is agreeing well or not agreeing well. That's not the point here, okay? The point is not the agreement. It's just look the general shape. Another point is that this mass is 10 times less from this to this, and to the two isomers. When you go to the big molecules, the big molecules has a lot of isomers. And the fragmentation fractions, you can see here, for some fragments, can be very different from one isomer to the other. So we have to be careful to, when you do the target tree, to know that which isomer are you really using, because then you get a mess. And second point is that this pyrimidine has one fragmentation matrix, and the pyridazine has another fragmentation matrix, because this, the masses are different. So that's the second point in this graph. And the third point that I put here is to get the eye, is that this mass, 51 here and 53 here, shows a different behavior. The cross-section here, for this mass, they come and suddenly it goes up. And there is a kind of inflection point at some point of here. So the shape is, for this fragment ion, is different from the others. And I show you now that this changing shape, the appearance of inflection point, is a signature that we are going to the inner valence shells. So now, inner valence shells, we start to do with Auger process, and again, we start with water. So this is the two-way one. This is 36 electron volts. And now I have a competition when I make a vacancy here. Either it goes promptly and emit an oxygen or hydrogen, or it has time enough to make an Auger becomes double ionized and generate this kind of ions. This is on dashed because we didn't measure this hydrogen plus hydrogen. We just measured these two. So now we have an Auger process, and I have some fragments that are originated from double ionization. And this fragment is essentially oxygen. The oxygen ion is always produced by this orbital. In the circles are the experimental data for the O plus H plus channel. But what I want to show here is that there is an inflection point. In this side, you have the Auger dominance and two double ionization. And this inflection point occurs because the projectile double ionization start to dominate the process for the fragment, give these two ions. Here's a set of oxygen production. This line is the Auger O plus by H plus. This is O plus single vacancy calculated with the single vacancy model. And these are the experimental data which do not agree. And that's the point, do not agree. Do not agree because you have here the inflection point, and here you have the increase of the cross-section with respect to the single vacancy one because the projectile double ionization. I have to go fast. Okay, so this is the set of the water. The outer shells, single vacancy and one concavity, clear. Inner shells, two concavities, one inflection point. And just for the total cross-section, you can see by simple visual inspection if the fragment is generated by the outer shell or inner shells. I show here a work from Claudia and Roger Miraglia, and this is very similar to what happened in atoms. See, the neon plus is a single concavity, and neon 2 plus has an inflection point here, because you have the Auger dominance in this point, and here you have the... so it's quite similar in atoms and what happens here in molecules. Again, I put here the water and showing that, well, also for the other H plus and OH plus, there is still an indication of the inflection point, and in fact, OH plus and H plus also comes from double ionization, but the majority of these two ions come from a single valence production. So it's a mixed process. In the case of oxygen, it's just one. Here I put the electron, 3 minutes. Here I put the electron. This clearly shows that the single vacancy is generated, the electron is generated by the 2A1, because the threshold, you have a high threshold. It's very nice to have the electron measurement. But on the other hand, the electron do not show clearly the inflection point because the maximum of the cross-section is near the inflection point. So protons is a kind of special in this visual inspection for the identifying the double ionization. Here I show heavy ions. Heavy ions is also not good for this, in this case, for this identification, because for other reasons, at low energy, captures start to get flux for ionization, and the cross-section ionization goes down. Here again, lithium 3 plus, I put carbon 3 plus to make a comparison with neon, which has the same thing, same behavior. Lithium and carbon are different because the screening of the carbon are different from the screening for lithium, but you see oxygen, the behavior of oxygen and the behavior of neon is quite similar. So we have a really a very similar stuff here. Again, now I put another mass that I didn't put before, this mass 38, which show clearly that we are there is an inflection point here. We are completely off of this shape, that's one concavity shape. Yeah? And this mass 38 for both pyrimidines and pyridazine are probably generated by inner shell orbital. And that's why there is also no difference between one and the other. Again, pyrimidine and electron impact. Now you see that the maximum of the electron impact is far from the inflection point, and that's the reason that is in this case, electron is also good enough to make this visual identification. And why that happens? Because the pyrimidine has much more electrons than water has. So the ratio of double ionization for single ionization is much larger in pyrimidine than in water because you have more electrons to double ionize. So then the inflection point shifts to high energy when you have much more double ionization. So you can clearly identify it. So 40 seconds. So that's the conclusion. Outer valence shell vacancy gives the most abundant fragments. Single vacancy model is enough to give a broad and good description of the fragment cross-section, and the cross-section curve shows no inflection point. Inner valence shell vacancies, less abundant fragments. Single vacancy is not enough to give a broad and good description of fragment ion cross-section. Cross-section curve shows an inflection point. Auger decay plays an important role, and double ionization plus gives a very important role also. Thank you very much for your attention.